Good. Elaborating. Welcome everyone. Today we have the pleasure of having Adam Grace. We will talk about stress in quantum systems.
Thank you for the introduction. And thanks everyone for coming the day before Thanksgiving, before your travel to see family. So I'm going to give, I guess, a little bit of an unorthodox talk. I'm going to talk about something that is kind of a hot topic in our field, but I'm going to talk about it from perhaps a bit of a fringe perspective. I'm going to talk about pressures in small quantum systems. The reason for talking about this is that pressure in the proton and in other hadrons, but especially the proton, has become a really hot topic, especially at JLab. Folks have been promising that these pressure distributions can tell us a lot of interesting physics. It could potentially tell us about the distribution or possibly even the nature of the forces inside the proton. Perhaps it could tell us something about confinement or the fact that the system doesn't collapse into itself. Maybe it could tell us something about mechanical stability conditions. And JLab has been kind of a nexus for this. A lot of the empirical extractions of these pressure distributions are happening at JLab. Volker Latifa and FX got a Nature paper in 2018 that I took this figure from of pressure distributions inside the proton. There have been press releases at a fairly recent all-hands meeting a month or two ago. David Dean mentioned their measurements in an all-hands meeting. More recently, Buju Duran et al., Zenadine Sylvester also on this paper, did an extraction of the gluonic contributions to these pressures. So that's all very exciting. However, the idea that these things that we're measuring are actually pressures has been challenged by some folks. The most prominent challenge comes from Shandong-ji and his collaborator. They basically claim that although you can call it the stress tensor, you can calculate matrix elements of it, you can extract these gravitational form factors as they're called, do Fourier transforms, whatever. They claim that they don't actually give pressures. They claim that these are momentum current densities and should be understood as momentum current densities and not as pressures or force distributions. On the other hand, despite this challenge, a lot of prominent theorists, Polyakov and Schweitzer, have the kind of standard review that everyone points to. But also Cedric Lorset has very vigorously defended the interpretation of these things as actual pressures. So we have some pretty smart folks on both sides who are claiming, on the one hand, that it's not really a pressure distribution, on the other hand, that it really is a pressure distribution. Who's right and how can we determine it? So my talk is going to try to give an answer to this from a rather unorthodox perspective. The spoiler is already in the abstract. I believe that the stress tensor actually does tell us about pressures inside the systems. On the other hand, I'm going to disagree with what some folks in the field are saying about these pressure distributions, some of the conclusions that they've made. So the way that I'm going to go about this is I'm going to give this talk in 3 chapters. First, I'm going to talk about stress in classical systems, basically to review what the stress tensor normally means in the familiar world of everyday objects. Next, I'm going to look at the hydrogen atom as a simple example of a quantum system and calculate all the things that people call stresses in it, the gravitational form factors, the infamous D term, and whatnot. And then I'm going to look at, this is where the talk gets unorthodox, I'm going to use the pilot wave interpretation of quantum mechanics to try to build a bridge between these. So first, stress in classical systems. The stress tensor ultimately comes from a bigger operator called the energy momentum tensor. It's a rank 2 4 tensor in relativity, so a 4x4 matrix, and this 3x3 submatrix is the stress tensor. You have an energy density, energy fluxes, momentum densities, and this. In parity to how these components are the flux of the energy density. The stress tensor can be understood as the flux of the momentum densities. You can understand this from the perspective of the continuity equation. For a closed system, your divergence of your energy momentum tensor is zero. And if you look at the spatial components, nu equals j, and you take the integral over some spatial region and put it into integral form, what the continuity equation tells you is that the amount of momentum in some region of space is changing by an amount that depends on how much of this momentum flux density is entering or leaving through the boundary. Now, there are actually two ways that momentum can change in a region. One of them is you can have particles going through some boundary, entering the region or leaving the region. Particles carry momentum into or out of the region. I imagine that this is what Shandong was thinking of when he said that the stress tensor should be interpreted as a momentum current density. On the other hand, we know from Newton's second law that if you exert a force on something, its momentum changes. So another way that the momentum of a system can change is if a force is exerted on the boundary. So the stress tensor basically includes all momentum fluxes. It includes changes in momentum in your system, either from particles going through the region or from a force being exerted on the boundary of a region. So in principle, technically, both groups can be right. It can be either particle flux or forces. That raises the question of, if it's even meaningful to ask, which of these two things, possibly both, is going on inside of hadrons when we measure the stress tensor. So actually, another point I want to make is that this is strictly positive. Or at least the diagonal components, which are pressures, are strictly positive. Your velocity and your momentum in, say, the x direction are both going to have the same sign. So your contributions to your stress tensor from particle motion are going to be positive. Your forces, because you can either pull on or push on a boundary, can be either positive or negative. Yeah.
Can I ask at this time already, when you talk about force, do you mean an external force, that your system is no longer closed but coupled to some external force, or do you mean something like that the system is divided into cells and then one cell exerts a force on the next one? Or?
That's a great question, and the second is exactly what I mean. In principle, you can have an open system and you have both kinds of forces operating, but the stress tensor strictly encodes forces acting between the cells. That's actually probably something I should have had a slide on, but that's a very good question and a very good one. An example of a positive force that everyone's familiar with is hydrostatic pressure. If you have some container of water, you're going to have microscopic molecules moving around, scattering off of each other, possibly pelting something you've tried to submerge in it, and that gets felt as a pressure. Because you have a gravitational force, there is a gradient in this pressure, with there being more pressure near the bottom, less pressure near the top. As an the stress tensor in this case is isotropic. It's just the pressure times a Kronecker delta. And if you take the divergence of this interesting thing, it will give you the gravitational force density. For an example of a negative stress, you can imagine something like a hanging Christmas ornament. You can look at one little bead, zoom in on it. It will have three forces acting on it that keep it stationary. One of them is the gravitational force acting directly on the bead. That's not part of the stress tensor. And then you have two things that are part of the stress tensor, the adjacent cells acting on your object. You have everything below it pulling down and everything above it pulling up, and all of these things add together to give you zero. The stress is strictly negative because you're being pulled on from both sides, and there's more stress near the top than at the bottom, in contrast to the hydrostatic pressure case where there's more at the bottom than the top. However, since it's negative, if you take the divergence of your stress tensor, you get the same gravitational force density. These are actually two examples of a more general law for open systems. The stress tensor encodes basically internal force between different cells of your system, as Christian said. And if your system, despite being open, is still static, that means the sum of these internal forces from these stresses and the external forces has to be zero. This is Cauchy's first law of motion for continuum systems. So basically, the stress tensor for open systems tells us about how these systems respond to external forces. It's important to stress that these external forces are not actually part of the stress tensor. They're the forces between small cells that you theoretically divide the system into. This works for a variety of continuum systems, including solids and fluids. It doesn't matter if the system is isotropic or not. There can be pressure anisotropies. It can be more complicated. It could be a liquid crystal. It could be a neutron star. Now, I want to show that these ideas are relevant to quantum systems too. And ultimately, from Cauchy's first law of motion, I'm going to argue that C bar rather than D is the really interesting gravitational form factor. So let's move on to the hydrogen atom as an example of a quantum system. So why the hydrogen atom? It's not a hadron. It's not the sort of thing we study at JLab. Kind of three reasons for it. One of them is that it's an iconic and familiar system. So if you want to understand stress tensor from the perspective of quantum mechanics, I think it's a pretty nice example to look at. G and Liu also considered the hydrogen atom in their criticism of this pressure concept. Another reason is we know how to actually calculate the stress tensor of the Coulomb field, of the electric field. The force field that's binding particles can also carry stress. It's how momentum and energy are locally transmitted. And for some rules, it's really important that we're able to calculate the stresses in the force field itself. Third reason is to avoid complications from relativity and quantum field theory. For quantum field theory, you run into issues with composite operator renormalization that can lead to confusion and in some cases controversy. Relativity, you get arguments about what spatial densities mean in relativity. By looking at a non-relativistic quantum mechanical system, I can avoid those controversies and just focus on the question of whether the stress tensor means something for quantum systems. And then kick the can down the road with regard to the other controversies. So do the usual barycentric separation. If you see me using Q anywhere, it's not a momentum transfer. It's the coordinates of the particles. And then big and little r are the usual barycentric and relative separations. Also, for all numerical results, I'm going to use the muon mass instead of the electron mass, just to make the mass balance less extreme. The plots look a lot nicer that way. So the stress tensor, you have some sort of operator and you sandwich it between momentum kets. And you write this out in the most general possible way that's compatible with the symmetries of the operator in your theory. The scalar functions that multiply the tensor structures you get are called gravitational form factors. Of course, this audience, you're all familiar with gravitational form factors anyway, but I tend to have a disclaimer when I mention them because some people get kind of scared when they hear it, that it's just a name and we don't use gravitation to measure them. You break down the energy momentum tensor into contributions from the constituents, and you get gravitational form factors for each of the constituents. In the case of the hydrogen atom, it's the electron, proton, and your electromagnetic field. There are a couple sum rules associated with these gravitational form factors. One of them is a momentum sum rule. If you take this A form factor at zero transfer, sum it over constituents, you should get one. Another one comes from the continuity equation. The C bar form factor is called a non-conserved form factor. If it is non-zero, that means your energy momentum tensor isn't locally conserved. So if you sum over the C bar contributions from all of your constituents, it should be identically zero in all momentum transfers. That doesn't mean C bar is unimportant. For individual constituents, it can be non-zero, and it will be really relevant coming up. Regarding what this momentum ket means, the momentum here is the barycentric momentum, the momentum of the hydrogen atom or your hadron as a whole. It implicitly contains some sort of internal state. In the case of the hydrogen atom, it would be your quantum numbers. In light of this, every state of the hydrogen atom is kind of a different particle. It will have different gravitational form factors. If you have orbital angular momentum, then it's a spin 1 or a spin 2 particle, and you actually have more gravitational form factors in that case. It's kind of analogous to how the proton and star, different sorts of excitations, are different particles and have different gravitational form factors. I'm only going to focus on the ground state here because it's easier, basically. So we have the wave function. We also need the operators themselves. For particles, for the electron and the proton, the operator I use looks like this. The curly brackets is the anti-commutator. The reason for using this operator, you can actually get it 2 different ways. One of them is you can write out the most general possible operator that's compatible with the classical limit, the V times P, and then require that when you sandwich it between free 1 particle states, the D and C bar form factors are 0, and this is what you get. Another way is you can take the classical expression and do Weyl quantization, and you get the same thing. Next, there's the stress in the Coulomb field. You can use the standard expression. If there's only an electric field, no magnetic field, this is what the stress tensor looks like. Even classically, the only difference quantum mechanically is that the positions of the sources are operators. So it's a Q hat instead of a Q. Now, with these things in hand, you can do the calculations, you can get the gravitational form factors. As one example, this is the only slide in which I'm going to talk about the A form factor. Your A form factor is very simple, it comes out to a dipole for the particles, and the Coulomb field contribution is 0. The reason that it's 0 is because the Coulomb field involves only the position operator, the Q hat, and not the momentum operator. And you can kind of get a sense of why I use the muon mass instead of the electron mass here. Even in the A form factor, the muon's down here, protons up here. This falls much more slowly because there's an effective whole mass that is proportional to the mass of the constituent here. You wouldn't see this at all if I use the electron mass. So this is basically kind of a mass or moment form factor, and it's dominated by the proton because it's more mass. For the D form factor, it's a little bit more complicated. There's a monopole and there's this non-analytic function, but you get something. You can also get a Coulomb field result. It took me a while to actually get an analytic form for it, and it's so complicated that it's not even worth showing. But here are some numerical plots of what they look like. This is finite at 0 momentum transfer. You can do a Taylor expansion of the architecture to convince yourself of it. But one of the interesting things about these is that these functions are strictly positive. This contradicts a very popular negativity conjecture. A lot of people assert that the D form factor at 0 momentum transfer has to be negative for stable particles. That's a necessary stability condition. However, I find for not just the total D, but for the contributions from each of the constituents, D of 0 is positive. These are the results. I'm not the first person to find this. G and Liu did their own hydrogen atom calculation previously. Their calculation's a little bit different in that they assume a stationary proton, effectively infinite mass, so they use the electron mass as the target mass. The reason they do that is because they then consider quantum field theoretic corrections, and trying to do quantum field theory with barycentric separation is complicated, so that's.
Can you explain what stability condition means?
So stability condition, actually, it's a little bit unclear to me, but the way I've always interpreted it is that they say that if you try to do a calculation for a potential state that might exist and D0 is greater than 0, then you shouldn't actually observe that particle in nature because it's not mechanically stable. Whereas for things like the proton and pion that actually are observed in nature, D of 0 should be less than 0.
But is that has to do somewhat with the existence of the bound system, or?
It's a little bit unclear to me, actually. What
It's just definition?
I don't know.
Okay.
there a classical explanation of some mechanical system would fall apart if it had the equivalent object being positive?
So, I didn't prepare a slide on this, but, Peter Schweitzer likes to give illustrations along these lines. I think all this, stuff I can erase, right?
Yeah.
Oh, I shouldn't have erased those patterns. Oops, someone else can fix it later. So, I do have a slide that talks a little bit about, part of this later, but if you do a Fourier transform of the D term weighted by the appropriate factors, and you take the isotropic component of it, then you might get something that looks like this, that goes positive and then negative. Kind of like in the plot at the very beginning here. Something that goes positive, then negative. The isotropic component of the Fourier transform of the D term has to integrate to zero. Peter Schweitzer and then some other folks after them started calling this the von Law condition. But basically, the reason for this integrating to zero is because the D term is multiplied by deltas. So you take the Fourier transform, then you integrate the Fourier transform. That's the same as evaluating this at delta equals zero. You're multiplying by delta, so you get zero. So there's this idea that the isotropic component of it has to be positive closer to the center, has to be negative further away, because positive pressure means pushing, negative means pulling. To prevent yourself from collapsing, you have to have outward pressure when you're closer in, and you have to have negative pressure pulling in when you're further out. So if you take something that's positive, negative, and you weight it by r squared and integrate it, you should get something negative. And if you weight by r squared, that's the same as differentiating this twice with respect to delta, evaluate that at delta equals zero, and you're going to get d zero. So that's basically the argument for why D zero has to be negative. In a nutshell.
Since we're discussing this now, if you take this literally as a pressure, then any system that has a gradient in pressure or some transition from positive to negative pressure, the boundary between these regions should move. There should be a force between them.
So
I mean, I don't really understand the stability argument. I mean, mathematically, it's absolutely clear that as you say, the form factor multiplies this kind of quadrupole structure, and it has to vanish in momentum space, and therefore in coordinate space, it must have alternating sign. But what does that mean for pressure?
I think it's a little bit wishy-washy, and kind of the reason I didn't prepare any slides with this argument is because it feels wishy-washy to me, and I kind of just wanted to skip over the wishy-washy stuff. As far as gradients and pressure go, taking the gradient of the pressure is what you do when you have an isotropic system. When it's anisotropic, you take the divergence of the stress tensor, which for an isotropic system becomes the gradient of the pressure, because you're taking the gradient of a Kronecker delta times the scalar function, becomes the gradient. When you take the divergence, this part vanishes, because the divergence in momentum space is just delta dot something, and delta dot this is zero. So the only thing that actually contributes to the force is C bar, not D. So I kind of see D as irrelevant to mechanical stability.
Before you go on, can I ask a question about your statements about the hydrogen atom?
Yeah.
So you said that the Coulomb field does not contribute to the A form factor?
Yes, this is, yes.
This is because you said it's a function only of the coordinate operator?
Correct. That's exactly why.
What does that mean physically?
It means that for this configuration, of course, there are going to be higher order corrections from quantum field theory, fine structure, ultrafine structure, which could change this. But at leading order, when you just have two particles bound by Coulomb's force law, the electric field isn't carrying momentum. And the reason it's not carrying momentum is because you have no magnetic field. It's E cross B that gives you your momentum.
It's just interesting that, I mean, this is exactly the opposite as we have in a ultra relativistic hydrogen atom, fast moving, where we have the Weizsäcker-Williams paradigm, where the Coulomb field projects on transverse photons, which actually carry light front momentum in the
That's interesting.
in the hydrogen atom. I mean,
I actually don't know anything about that calculation, so I can't comment on it.
this means it's somewhat like a pure force. It doesn't carry any momentum.
It doesn't carry any net momentum, but it carries stress, which is kind of a way that momentum is transmitted.
And even going back even further, the form of the stress operator now, is that unique, or are there any ambiguities in constructing this operator in the first quantized approach?
This one, oh yeah, it's absolutely ambiguous. First quantization is a completely mathematically ambiguous procedure. I actually, in the paper draft I'm writing, I start out the section with, unfortunately, first quantization is an ambiguous procedure and there's not a unique. And then I give some examples of things you might think up off the top of your head that seem equally valid. And then I go through the argument for why I would use this one. And basically, the argument that I find the most convincing is that this is the operator that gives you a D term and a C bar of 0. But it also happens to be equal to what you'd get by Weyl quantization. But it's absolutely not unique. Whenever you have an operator with a very complicated dependence on both position and momentum, first quantization of the operator is ambiguous. You can come up with infinitely many operators that have the same classical limit and are Hermitian. This seems the most physically sensible of the infinite choices to me.
The sum rules you listed for A, so is this satisfied for your hydrogen arrow?
Here.
Yeah, so
Yes, it is satisfied. And actually, it's kind of straightforward to see from the formula. This is 0. At 0 momentum transfer, since this is proportional to delta squared, this just becomes 1 at delta equals 0. So you have mass of E over M, mass of P over M, and M is just ME plus MP. Of course, this is non-relativistic quantum mechanics. M is the sum of masses. It doesn't include a subtraction of binding energy.
So the sum rules are already kind of baked into the decomposition of the unit. So is that right?
I'm not sure what do you mean by baked in?
So you didn't impose anything here to satisfy the sum rule.
Oh, no, I didn't propose it. It just comes out.
Right. That means that somehow the decomposition of the tensor already knows about that.
It was baking
I mean,
opposite of it, right?
the physics should know about the principles from which this follows. Ultimately, your conservation laws follow from symmetries, and as long as you're keeping those symmetries the whole time, the conservation laws will follow.
So is the conservation on the energy moment tensor?
Yes.
Okay. Okay.
Since I'm only looking at the momentum flux density components, the stress tensor, momentum conservation is the relevant thing, so spatial translation symmetry.
Question, for the decomposition of the form factor somewhere or another. You made comment, okay, go back where you make the comment that you're only going to focus on the ground state.
Yeah.
But you had the Wigner-Eckhart theorem, right? So you could relate the excited, what I would call the excited states to the ground state anyway, or rather just the unique matrix element. It's just angular momentum factors. It's just angular momentum factors.
Wigner-Eckhart works for different angular momentum projections within the same partial wave.
Yeah, so it would be like excited to a ground or something. That's what I was referring to.
I mean, excited to ground is new dynamical information compared to ground.
That's what I was asking. That's what I'm asking.
I'm actually not familiar with that theorem, so I don't know, but yeah, this is only the L equals 0 state.
It's because you made the analogy to a proton or another. Well, like here it would be, you know, the L equals 1 to an L equals 0, a P wave transition, something like that. That's what I was thinking.
I'll have to look into that. That might actually make, because in the future I want to do the entire spectrum. It seems a little bit daunting, but if there are tricks to make it easier, that would be nice. Okay, so where was I? I talked about this. Okay, C-bar next. C-bar, the one that I like the most, the one that I'm excited by. C-bar, strictly non-analytic function, it has this arctangent. But again, you can just do the Taylor expansion and convince yourself that this is finite at 0 momentum transfer. The local sum rule is satisfied. If I take the C-bars of all 3 constituents, they sum to 0. I didn't impose that. I calculated the matrix elements for the operators I showed earlier. And once I work them out, they sum to 0. I didn't use this as a definition. It just, when I worked it out, it happened to be equal. So basically, I wouldn't say that it's baked into the decomposition. I would say that the formula for the stress in the electromagnetic field is smart enough to do this. But yeah, you get this nice thing. The C-bars of your particles are negative. It's pretty well known in hadron physics that C-bars of the quark are negative. C-bar of the gamma, just like C-bar of the gluon and hadrons, is positive, and they all sum to 0. Now, I'm going to slightly change the focus to coordinate space from momentum space. One of the reasons that people are really interested in form factors is that Fourier transforms of them can be related to coordinate space or impact space distributions. Since this is a non-relativistic system, there are no ambiguities about light front versus bright front or anything. This is pretty straightforward. These are spatial densities. There's still the interpretation of whether the spatial density should be literally interpreted as pressures, but they're spatial densities nonetheless. So there are 2 components to this. There's one that involves a Fourier transform of the A form factor, and then it's weighted by these 2-sided gradients. So that basically tells you about something that smears out wave packet dispersion, since you have these gradients. And you have this other thing, this black letter Tij, this little Tij, which has your D and your C-bar form factors. So I would call these dynamic stress and internal stress. Dynamic stress is kind of like if you walk into a wind tunnel or there's a fierce blizzard and you feel it blowing against you from one side. You're feeling this one-sided pressure. That's dynamic stress. This is stress due to the fact that you have your wave packet dispersion. Your wave packet is moving as a whole. Now, if you go to a frame that you're moving along with your wave packet so you no longer feel it, you still have stresses acting on you from all sides. These are the internal stresses, and they're kind of the things we're interested in and why we talk about the D form factor as opposed to the A form factor when we talk about pressures. So these are due to internal motions or forces. I'm going to just focus on this internal stress. You're not going to hear about the A form factor again. So you have this internal stress formula. Something I'd like to stress is that involves both D and C-bar. There isn't really any a priori justification for dropping C-bar unless you sum over all the constituents, in which case it cancels out. Once you have this, we still haven't established that this should literally be interpreted as a stress distribution in quantum systems. Let's call it a pressure anyway, so we have a word for it. You can project out this pressure, whatever it might be, into different directions. The thing people like to do is they like to project out onto the radial direction or onto some tangential direction, call these radial and tangential pressures. They might be forces, they might be particle motion, they might be a mix of both. Maybe the question is meaningless in quantum mechanics, but let's just call them pressures so we have a word for them. And these are the formulas that you get. If you go and calculate them for, say, the electron or the muon, this is what you get. It's strictly non-negative. It's strictly tangential as well. The radial component, the radial pressure vanishes in the hydrogen ground state for your particles. There's a little wiggle here because I did this Fourier transform numerically. I don't want a little result that's analytically exactly identically zero. So you only have a tangential stress. Now, if you were to interpret these pressures as particle motions, what this tells you is that in your ground state, your particles are moving completely circularly around each other. That's very weird though, because the ground state is a L equals 0 eigenstate. And as an eigenstate of the orbital angular momentum, it's not something that on average has no angular momentum. It has exactly 0 angular momentum. Now, of course, we could say that, well, particles don't really have trajectories, so we can't really apply these classical concepts. But if you try to apply classical concepts of forces in motion, it doesn't really make sense to say that your electron in the ground state is orbiting the proton in a circle. So the stress has to be something else. It has to actually be a stress, I would think. And the radial stress is also 0, so you don't have a particle moving back and forth through the proton either. Very strange. We can also look at the stress distribution for the Coulomb field, both the radial and tangential projections of it. For these masses, at least the proton and muon mass, the radial stress is negative, the tangential stress kind of oscillates a bit. These numbers are much bigger, note, going up to 400 keV for the egometer cubed, versus over 40,000. The Coulomb stress dominates the particle stresses by a significant amount. And the radial stresses are negative, which is kind of analogous to this hanging Christmas ornament. Your Coulomb field feels like it's being pulled, not like it's being pushed. So I kind of want to stay on the Coulomb field for a little bit because there's something kind of conceptually significant. Possibly to a lot of people, this will just be common sense, and I'm not saying something really interesting. But when you take the expectation value of the square of something, it's not the same as the square of the expectation value. So the stress in your Coulomb field isn't the same as what you'd get from the stress of a classical source with the charge distribution of the hydrogen atom. So you can't say, calculate the expected value of the electric field, then apply this formula, and that's the expectation value of your Coulomb stress operator. This can be illustrated especially starkly if you look at a mass balance system. Pretend that the proton mass and the muon mass are the same for a moment. The charge density is going to be identically 0. This is something that we all know very well, especially folks who have calculated electromagnetic form factors of the neutral pion, for instance. You have constituent charge densities that just cancel out. And if you take the expectation value of the electric field, it will likewise be 0. But you don't square the expectation value of the field. You take the expectation value of this question. And the Coulomb stresses continue to be non-zero even in charge balance system. That's kind of a point that I want to emphasize, and I'll go back to that in a moment. It's actually kind of a nice segue as well into kind of the fringe component of this talk. I'm going to talk about interpreting these stresses in the pilot wave formulation of quantum mechanics. So for those of you not familiar, the pilot wave interpretation ascribe.
Before you get there, one question. When you talk about gauge fields or the Coulomb field contributions to the stress or the A form factor, what's the role of gauge invariance in this? Because
make things easy, I've chosen to completely ignore it. You can always go to a gauge. So the way that I've actually done the calculation is I've used the phi field in a lot of places and said that E is minus the gradient of phi. You can always go to a gauge where the phi field is 0 and instead you get the E field from the time derivative of your A field. That would make some of the calculations more complicated, and I've chosen not to look at that. So I don't really have an answer to your question. I've just chosen to ignore it.
So the statements you derive are for one particular kind of gauge fixing in the, or gauge condition in the barycentric frame.
I actually don't know to what degree the conclusions depend on gauge because I've chosen not to look at any gauges. They might not.
even what you said earlier about the division of A between particles and the Coulomb field, it might depend on the gauge, isn't it? I mean,
Yeah. The big complication, of course, is when you have this particle stress depends on your P operator. If you change the gauge, then the P operator gets an A in it through minimal substitution. And should you consider that now to be particle stress or Coulomb field stress? I don't have a good answer to that. I have chosen not to look at it to keep things simple for myself.
yeah, I mean,
That is something that I should address down the road.
even at the very beginning, when you posit the first quantized stress operator, these momentum operators can, in a gauge theory, they can pick up.
Yeah, they pick up an A field by minimal substitution.
Exactly, yeah.
So I don't have an answer to it. I'd assume that to get all the same conclusions, after you do a gauge transformation, you have to shuffle those terms back into what you're calling the Coulomb stress. That's something I should look at, but I have not, so I don't have a good answer for you. I've chosen to just use the standard phi only gauge to keep things simple for myself. Yes.
Following up on that, it'd be possible to choose like a unique stress tensor or maybe even non-unique stress tensor that's gauge invariant, so you wouldn't have to worry about that. Certainly in QFT, we could do that, but.
You know, actually, that might solve the problem, because. So the way I got this formula is I just used the standard gauge invariant formula. F mu rho, F rho nu, plus 1/4 G mu nu F squared. And I looked at the case in which you only have an E field. And of course, whether you have a B field or not is gauge invariant. This is a gauge invariant expression. So yeah, actually, it should be gauge invariant. I should check in more detail to be sure. Christian raises an important point, but.
If you remember the debate about the definition of quantum field theoretical angular momentum from like 15 years ago, people try to do exactly that. A gauge invariant energy momentum tensor, and it leads to very non-obvious physical conclusions regarding the angular momentum. So you can define it in this way, but then you have to follow through on what it means for some quantities. It may not be so obvious.
Yeah, that's a good point. It's something I haven't really thought about, but it's something I should think about.
So I don't want to open up kind of worms, but isn't that the same thing about like what's the scheme choice for renormalization? So
It's not unique.
characterizing a system. I remember Elliot Leader telling me one day that it's just like deciding what's your system of coordinates. You cannot describe a system unless you choose your system of coordinates. And so to me, within that particular system of coordinates, quote unquote, choice, this is how the system looked like. It had a meaningful concept. If you move at the speed of a car, or the car is not moving, okay, the description of the system changes.
Yeah.
But to sort of, I heard this story over and over. Oh, your choice of gauge will change your conclusions about the system. And it seems like it's an endless loop. And I'm asking is, why do we care if you have to always make a choice?
There might be a physically sensible choice, just like there's a physically sensible choice of coordinates in some cases. Even things like the dynamics of the solar system. You can use an Earth-centric frame. Of course, we're not medieval geocentrists, but if we wanted to make our lives a nightmare, we could use that frame, and it'd be equally valid according to the general coordinate invariance of general relativity. But there's a frame that makes more sense, and it's the one in which the sun's at the center. You'd get the same physical conclusions, but yeah, maybe there's a sensible choice of gauge. Maybe I should try to make this gauge invariant. I haven't really thought about it, so I don't know, but these are important considerations, and I actually really appreciate all these comments. Anyway, how am I doing on time? I have 15 minutes left. Going to talk about stress in the pilot waveform. quantum mechanics. I actually managed to get a much nicer version of this plot by using a different wavelength, but I finished it after I sent in my slides, so you're stuck with this. So the pilot wave interpretation of quantum mechanics is basically a reformulation of quantum mechanics, or maybe even not a reformulation. It's another way of looking at quantum mechanics. I could say like how Lagrangian or Hamiltonian dynamics is a different way of looking at Newtonian mechanics. You basically have the same underlying theory, but you choose to emphasize different mathematical structures. And you kind of assign both positions to particles, definite positions to particles at all times. You just don't know what they are. And you say that the wave function is really there and it guides the motion of these particles in a way that's ultimately done by Schrödinger's equation. This was actually first discovered by de Broglie. I apologize for mispronouncing his name. I'm terrible with French names. It was never published because Wolfgang Pauli basically kind of bullied him into submission and giving up on it. But it was rediscovered by David Bohm in 1952, published in 2 papers in Physical Review. So because David Bohm was the first person to publicly advocate it and to publish it, it's often called Bohmian mechanics. Some people call it de Broglie-Bohm pilot wave theory to give credit to both of them. But both of them discovered it. So the idea behind it is that your systems always have definite configurations at all times. They evolve according to definite trajectories. When you do a measurement of position, you're just revealing something that pre-existed. You're not causing a instantaneous collapse of a wave packet into sharply localized. The wave function is also really there, and the wave function guides the motion of the particles. So the most popular icon of Bohmian mechanics is their illustration of the double slit experiment. You have a wave packet that goes through, you have single slit dispersion happening, diffraction happening, and then you have interference between both of them. And then your wave guides particles. I drew a bunch of different trajectories. They look a little bit wonky because I'm just learning how to use Matplotlib stream plot. But your wave guides the particles on these very weird counterintuitive looking trajectories that they might suddenly jump. But they end up getting a distribution that looks like the diffraction pattern that you would expect. Formally, the way that it is done is you take your wave function and you do a polar decomposition of it. A real valued modulus function R, a real valued phase function S, and you turn the Schrödinger equation into 2 coupled equations for these fields. One of them, basically governing the phase function, looks a lot like the Hamilton-Jacobi equation, suggesting that when your system is in a particular configuration, the gradient of this phase function evaluated at that configuration might be the particle's momentum. You also get something that looks like a continuity equation with the modulus squared as the effective probability. The velocity appearing in this continuity equation is just the same thing that looks like a momentum in the Hamilton-Jacobi equation divided by your mass. So these both suggest kind of the same velocity. And if you start with some particular position, they uniquely determine the trajectory of the particle. Some weird things there. All right. So regarding this momentum that you get, it's a very peculiar momentum. This is not the same momentum, same canonical momentum corresponding to your momentum operator in ordinary quantum mechanics. What you might call a hidden variable. There is one exception to this. If your system is in a momentum eigenstate, then this P is the momentum, it is the eigenvalue. And it's pretty straightforward to see. The phase of your wave function for a momentum eigenstate is just Px. You take the derivative with respect to x, you get P. But in general, measurement is actually a physical process, and you can calculate the way that measurement changes the system. And if you do a measurement, momentum measurement, it actually changes your system, gives it a momentum. The momentum that it's given is the same as the momentum you measure, but it wasn't a pre-existing property. It's created by measurement. So the pilot wave interpretation agrees with Copenhagen. with respect to all observables except position. Now, one of the really weird things about pilot wave theory, this is something that is one of the reasons that a lot of people don't like it. It's one of the reasons that Einstein gave for not liking it, despite him being an opponent of standard quantum mechanics, is that if your phase function is 0, or even if it's constant, if you have a real wave function or just a wave function with a constant phase, then your hidden momentum is 0. So your particle's just sitting there. This is true for the hydrogen ground state. It doesn't have a changing phase that depends on space. So you can imagine it's technically actually a still image. You can pretend that this is an animation of what the proton and the electron are doing according to pilot wave theory of the hydrogen ground state, and it would be what you'd expect. It's not moving. How could this possibly be? Well, it's because of what's called the quantum potential. My clicker doesn't work anymore now.
You know, maybe click on
Yeah,
the,
you,
I think you
Back
can
into the-
focus on the,
you can do it, Adam.
is it on this computer?
yeah, just, yeah, click on the slides, I think.
Well, it's not working. It's not clicking, it's the keyboard arrows, okay. All right, so it's what's called the quantum potential. In the effective Hamilton-Jacobi equation that you get for the phase function, you have a part that looks like your classical kinetic energy, and with your classical potential, so this would be your Coulomb potential in the case of the hydrogen atom. But you also had this other term that depended on the Laplacian of your modulus function. So what David Bohm did was he decided to consider this a new potential that he calls the quantum potential. It has your h bar squared in it, and it's basically responsible for all deviations in quantum systems from their classical behavior. There are a bunch of papers out there from the Bohmian perspective using this to explain interference phenomena, using it to explain entanglement, quantum tunneling, all sorts of things. It's an extremely non-local object. You can see that it's divided by this modulus that you're taking the Laplacian respect to, so it doesn't fall off with distance the same way that the Coulomb force or the gravitational force would. It's also, this is a function of configuration space, not your empirical three-dimensional space. And that enables you to have very weird correlations between things that might be nearby in configuration space, but not actually nearby in empirical space. So this extreme non-locality, fun historical fact, is actually what inspired J.S. Bell to work on what became his inequality. It's also worth noting that J.S. Bell was a huge proponent of the pilot wave formulation. And I highly recommend his this book, which is a collection of all his writings about non-locality and quantum mechanics, philosophy, and whatnot. So you can do the polar decomposition for the wave function. You can also do it for anything that depends on the wave function. So to keep things simple, for the remainder of this talk, I'm just looking at the one particle case, not the two particle case, not doing the barycentric relative coordinate separation anymore. So for the one particle case, if you do this polar decomposition for the stress tensor, you get something that depends only on your momentum. This basically pi pj over m, it's your classical particle stress tensor, plus a h bar squared quantum mechanical correction that depends on the modulus of the wave function. So this is basically telling you about stress not due to particle motion, but stress due to the pilot wave. So for a static system in which this is 0, the expectation value or stress tensor is just telling you about stresses exerted by the pilot wave. So if you recall from a few slides ago that the particle stress in the hydrogen ground state is entirely tangential, your force diagram on the electron might look like this. You have Coulomb field force going towards the proton. You have quantum stresses tangential on the electron, and it's remaining stationary. That's kind of anticipating an objection to this diagram that these forces can't balance out because these are orthogonal, and I was going to say they're not actually orthogonal. If you have a system with some finite width, of course, the electron we all believe to be a point particle, but roll with it for a moment that it has some small but very tiny size, then what is tangential in one location and tangential in another location are different from each other. So your tangential forces can add together to give you a net outward radial force. Now, more formally, as opposed to this cartoonish picture, the way that you get the force from the stress tensor is by taking the divergence of your stress tensor. So applying this at the level of expectation values, because all we have empirical access to are the expectation values. The actual configurations are hidden variables, after all. You take the divergence of your stress tensor, which is entirely tangential, and you recall that your unit vectors in the tangential direction, unlike your Cartesian unit vectors, depend on space-time location. So this divergence isn't zero. In fact, fun little algebra problem you can do. This divergence is entirely radial. So that's how you get a radial force out of a tangential stress. So we have an open system. You have kind of internal stresses from the pilot wave, and you have an external force, Coulomb force, and they balance out. So since it's also static, since there's no motion, Cauchy's first law of motion, which applies to static systems, should work. We apply it to the ensemble average, the expectation value, since that's all we have empirical access to. And the external force density acting on your system should be equal to this divergence. If you actually work this out, as was brought up earlier, the D term doesn't contribute because it is divergence free. You end up getting this gradient of a Fourier transform of the C bar form factor. And it works out to be equal to your probability density times your Coulomb force law. This is B, the impact parameter. Is different than the relative separation, but once you take the masses into account, this quantity is just equal to the relative separation. So it's alpha over R squared. This is the Coulomb force law. So basically the stress in your system tells you how it's responding to an external force. And information about this external force is hidden inside of the C bar form factor. In fact, I have so far been able to show that for general two-body systems. I don't have an n-body generalization yet, but for two-body systems, independent of whether they're static or not, so this includes states with orbital angular momentum, this gradient of the spatial C bar Fourier transform of C bar is going to work out to be a probability density times your force law. So in principle, if you could access your C bar form factor and you can access your probability density, you can reconstruct the force law. Of course, this is for a two-body system. It's still unclear to me if it generalizes to n-body systems. And it's unclear if there's a relativistic generalization too. It might be tricky in particular to use the concept of probability density relativistically. It might actually require going to the light front. My gut feeling is that GPDs are probably going to need to be involved because they give a probability density interpretation in transverse position space and longitudinal momentum fraction space. But again, this is something that actually needs to be worked out. Open question. What about the D form factor? That's the thing that people are typically very excited about. Well, the individual constituents D form factors aren't really that meaningful. They can give you pressure anisotropies because C bar is entirely isotropic. They don't give you the actual stresses. C bar is part of the actual stresses. However, if you sum up all of your constituents, the C bars cancel out, and that's when your D form factor is meaningful. Something to stress, though, is that the net external force density, once you've summed over all your constituents, is zero. Your proton with everything in it, your hydrogen atom with everything in it is a closed system. So once you take the divergence of this, you get zero, and mathematically it follows because this is divergenceless. Oh, I forgot a complex exponential here. Oops. So the D form factor does not tell you anything about the force law, and I don't think you can learn anything about confinement or the nature of how QCD is operating from it. I think C bar is where you really get that from. So that's where I promised I would disagree with some other researchers. One last, I'm kind of out of time. Well, one last thing, I'm close to the end. I want to talk about is that the Coulomb stress. A little while ago, I talked about how when you have a mass balance system, the expectation value of the charge density is zero, expectation value of the electric field is zero, expectation value of the square is not zero. Understanding that absolutely does not rely on the pilot wave interpretation at all. But I think the pilot wave interpretation at least is kind of a nice illustration because it says that although you don't know what it is, there is a definite configuration and every atom is different. You might have one atom that's in this configuration with the proton here, electron here, one here, and muon here, anti-muon here. And just as often, you'll have the opposite configuration in a mass balance system. So once you take the ensemble average, the charge densities are going to cancel out and these electric field densities are going to cancel out. However, for the individual atom, the charge density and the electric field configuration are both non-zero and they both carry stresses. And the stresses, because they depend on the square of the electric field, are equal to each other. Kind of the hatch plot thing I did previously didn't look nice with this. So I just projected out one component of the stress. I projected out the component along the electric field line, which is strictly as one is greater than. So these are the same and the stress survives ensemble averaging, unlike the electric field itself. And I just want to illustrate that having a negative stress here is not really a problematic concept. It just means that there's some sort of pulling. And one way to think about it intuitively is if you have an electric field and a dielectric material, the charges in it are kind of being pulled apart. So to wrap up, since I'm kind of a little bit past time now, I have a few main conclusions. One of them is that the stress tensor can indeed be interpreted as providing access to stresses. In the pilot wave interpretation in particular, the particle stresses are stress exerted by pilot waves on the particles to keep them in place or guide them in their motion. And in the case of the hydrogen atom, at least, it's not clear if this generalizes at all to QCD, because QCD is a way more complicated theory. But the electric field stress is just the usual electric field stress that you take an ensemble average over different configurations. And you need both D and C bar to access the stresses from individual constituents. You can't just ignore C. I think that C bar is the most interesting form factor because it encodes the force law that's operating through Cauchy's first law of motion. Still unclear if this generalizes to a relativistic system, but at least non-relativistically it holds. Negative stresses are not a problem. They don't indicate mechanical instability. A stalactite hanging from a ceiling of a cave is not mechanically unstable. Those projectors hanging from the ceiling are not mechanically unstable. So that's fine. And the sign of D0 has nothing to do with mechanical stability. I'm not the first person to say that. Other folks have been saying it. G and Liu said this. They did the hydrogen atom calculation previously, and they said that. I completely agree with them. The sign of D0 has nothing to do with stability. There's still a lot more to do. I need to look at orbital angular momentum. In pilot wave theory, states with orbital angular momentum are not actually static, they're orbiting. So that might complicate things. So I still need to look at that. I need to incorporate intrinsic spin, something that is a difficult sticking point for Fermion mechanics, as Gabe likes to point out a lot, and work out possible relativistic generalizations. That will also be hard because relativity is also kind of a difficult point for the pilot wave formulation. Most likely, I'll look at it from the perspective of light front dynamics. And ultimately, I want to answer the question of whether C bar of the quark, if you were to extract it for a proton or a pion, can that tell you what the QCD force law is? Is it possible to extract? I don't know actually.
The pion has no C bar form factor. The pion as a whole.
I mean, if you sum over constituents, it doesn't. You can get contributions from the gluon and the quark separately.
As far as I know, no, not. high on decomposition of the matrix element of the energy momentum tensor has A and D.
There's also C-bar. C-bar exists for systems of all spin or no spin. Once you get to higher spin systems like spin 1 systems, there are actually multiple non-conserved quantities. There are 3 of them for spin 1, for instance, as opposed to just the one that you have for spin 0 and spin 1/2. But there is a C-bar for spin 0 form.
We can discuss this later.
And I'm going to thank you for your time and leave you with a list of resources that I found very helpful for learning about both the hadronic stress tensor and about the pilot wave formulation of quantum mechanics. By the way, the slides I assume will be online. These purple texts are all hyperlinks. So you can actually just click on them to get to the Inspire listing for papers and Amazon for the books. Anyway, thank you so much for your time.
If anyone have questions, please raise.
Can you elaborate more about the Broglie condition? Because on 24, on page 24, when I look at the radial pressures, they don't seem to follow the Broglie condition. Maybe it's just
Oh,
just looking at that.
the Van Looy condition. I'm probably pronouncing his name. Sorry. That is for the isotropic pressure. So it's average over all directions. So you would need, because there are 2 tangential directions in 3D, you would need to take 1/3 the radial stress plus 2/3 the tangential stress. That gives you your isotropic pressure, and it's that when you integrate it gives you 0. Yeah.
Questions?
Yeah.
Can you go to your conclusion slide?
That was, oh, I'm going the wrong way.
I think you had something, you mentioned things to do in the future. Maybe
Oh,
explain.
there we go.
Key suggestion. Maybe try and see if it would be a step in the water of relativity.
Mhm.
Try it without going into spin, just to avoid the complications. And yeah, you still talk about a relativistic system there. And as I said, it's kind of kooky, but then it might give you a little bit of a clue. Everything's actually started to try and come in. As I said, I was trying to make a simple step through spin. I mean, obviously the spin is the next important generalization, but I'm thinking Willis Lamb, of course, all that was because he did it perturbatively, but it involved the fact that he had spin electrons and then added in relativistic corrections, but it's a higher order sort of thing. He's doing approximation. Right, so won't have hyperfine splitting system.
Did you actually make use of the Bohmian framework in order to get the calculation where you have the stress law, the force law come out as being corresponding to an observable, or did you just use regular properties of the wave function in the Schrodinger equation?
So I didn't directly use the pilot wave formulation to do the calculation. Looking at the pilot wave formulation was what gave me the idea that it might turn out that way. Then I did the calculation. And I said somewhere that I have a general proof. Well, not really general, all 2-body systems, regardless of whether they have orbital angular momentum. That I did just using the Schrodinger equation. I didn't use the pilot wave formulation for that. The pilot wave interpretation was just what gave me the intuition to come up with this idea and then gives an intuitive explanation for why that should be the case.
Then you shouldn't necessarily expect any difficulties from spin and Lorentz invariance. If all you use is the general structure of quantum mechanics, you might get the same thing as like passing from phase-space distributions in a non-relativistic system. You just go over to basically Wigner functions in QFT. You might be able to do the kind of same straightforward transition.
It's actually a good point. that's a good point, thanks.
How do you expect your conclusions could change if you do all of the future work that you're planning to do?
You want what?
Do all of the future work that you're planning to do, if you include relativistic corrections or spin, do you think you could say, oh, C bar does not have all of the pressure now, it's not distributed amongst D as well, or?
So, the one place where I'm kind of concerned that the, idea of C bar containing all the force information like is once you go to more than two constituents, or if you allow the force field to carry momentum, which relativistically it does. Especially if you have a B field there, because then you can have E cross B. If that's the case, then the forces, say you have a multi-electron system and you calculate the C bar of the electron. Well, that's going to sum over the contributions from all of the different electrons, and thus any forces between the electrons will cancel out and disappear. And you're losing some information about forces acting on an individual electron from other electrons. The same thing would apply to quarks, the same thing would apply to gluons. So there might be information lost just from the fact that you're integrating out more information or summing out more information once you have a complicated system. And also when your force field carries momentum. So that's what I'm a little bit concerned about, it not necessarily generalizing.
Any more questions? Any more questions in the room? All right, if you don't have any questions, let's thank Adam again. Thank you.
Thank you.